Okay, here we go with our last example of a kinematics problem for this week. And this one's going to be relatively challenging because it's going to have several steps, an intermediate step that we're going to need to figure out in order to get to the answer. And it's going to involve freefall, which is another classic physics example, and it's pretty interesting because it's a real life kind of thing. So here's the example. So we've got a ball thrown vertically upward from the ground level at time t equals 0 seconds. At t equals 1.5 seconds, it passes the top of a tower. And 1 second later, after that, it reaches its maximum height. And the question is, what is the height of the tower? So I've gone ahead and put in our kinematic equations. And I've made a little picture of the tower. And I'm going to sketch in the situation of throwing the ball upwards and label the times that various things happens to get us started. So ultimately we're trying to figure out what's the height of the tower. That's our question. So the thing we're trying to get is the height from the ground up to the top of the tower, like that. And let's say we're over on this side. We're throwing this ball upward from the ground. It flies up, and at t equals 1.5 seconds, so t equals 1.5 is when it passes the top of the tower. 1 second later it reaches its maximum height, so that's t equals 2. T equals 2.5 is when it reaches the top, and then it comes back down again and comes back down to the ground. All right, so 1.5 to get to the top of the tower, 2.5 to get to the top, and then presumably another 2.5 seconds to get back to the ground again. And we're going to try and figure out from that the height of the tower. So how do we proceed? Well, this is a kinematics question. The velocity of the ball is changing as it flies. The reason the velocity is changing is because gravity is acting on it, and that's causing it, as it's on the way up, to slow down, and as it's on the way back down, to speed up again. But that acceleration is constant because the force of gravity isn't changing during this entire interaction. It's a constant. So there's just the one acceleration. So what is that acceleration? How quickly do things accelerate when they're experiencing just gravity? The answer is that every object near the surface of the Earth has an acceleration of about negative 9.8 meters per second squared. And it points downwards. So that causes objects that are falling to get faster and objects that are rising to get slower. And it's interesting that acceleration is the same for every object. It doesn't actually matter what the mass is. The reason that's true is something that we will learn about later in the term. So what do we do? Well, let's look at our equations. Average velocity and displacement. We don't know what the displacement is. Average velocity, velocity squared, acceleration, displacement. We don't know what the displacement is yet. That's one of the things we're trying to find. V final, V initial, acceleration, and time. Well, we do know an initial velocity. Let's write down what the things we know. We know the initial velocity is 0. So actually, let me make a table. We've got t and v. At time 0, the velocity is, I'm sorry, not 0. We actually don't know what it is, do we? We don't know. At time 1.5, that's when it passes the top of the tower. We also don't know the velocity. What we do know is that at time 2.5, it's 0. Why do we know that? Well, at the very top, the ball stops for just a moment as it turns around again. The velocity has to be 0. So we know the velocity is 0 at that one moment. and we know the acceleration is negative 9.8. So we don't know what the initial velocity was. Let me put that in a different color. That's the initial velocity, VI. And let me scratch that out a little bit more to make clear that I made a little mistake there. We don't know what the initial velocity was at the moment it was thrown, but it has to have been not zero, otherwise it wouldn't have risen in the air at all. The person down on the ground threw it upwards. So maybe what we can do is we can figure out what the initial velocity was. And then from that, we might be able to figure out something about the height of the tower. So I think that the equation we're going to want to be going after is this one right here. So there's an initial velocity that we don't know. There's an acceleration, which we do know. There's a time, which we do know. And there's a final velocity, which we know it was 0. That's the final velocity at the top. Let's go with that. So we've got final velocity equals initial velocity plus the acceleration times time. So we know that at the high point, the velocity is 0. That's the final velocity. Initial velocity we don't know. Plus negative 9.8 meters per second squared. And the time is 2.5 seconds. That's the amount of time it takes for it to get to the high point. Okay, so this seems like there's just one variable. There's only one thing I don't know, that's the initial velocity, and I can multiply 9.8 times 2.5 and I will get it. So I'm going to rearrange the equation. So I've got VI equals plus 9.8 times 2.5. And that's going to be, let me go over to my calculator and do 9.8 times 2.5. And I get 24.5 meters. No, not meters. 24.5 meters per second. So that means the initial velocity with which the ball was thrown was 24.5 meters. And it's plus because it was upwards per second. 24.5 meters per second. Okay, this is promising. I know what the initial velocity was at the moment that it left the ground. It was 24.5 meters per second. I know the amount of time it takes to get to the high point, to the high point of the tower. That's 1.5 seconds. And I know the acceleration. All right, so I've got another copy of the question and the equations, and I still know the acceleration is negative 9.8. I know the initial velocity now was plus 24.5 meters per second. I'm trying to find a displacement, a distance traveled to get to the top of the tower. So I want something that involves the displacement, either this one or this one. So I don't know the velocity at the moment that it passed the top of the tower, but I do know the initial velocity when it leaves the ground. I know the amount of time it takes to get to the high point of the tower. That's 1.5 seconds. I know the acceleration. I know the time. This is my equation right there. All right, so let me rewrite that. Delta x equals phi initial times time plus 1/2 at squared. So the initial velocity was 24.5 meters per second. And the amount of time it takes to get to the high point is 1.5 seconds. Plus 1/2 times negative 9.8 times the time squared, that's 1.5 seconds squared. Delta x. So the displacement is going to be the result of doing that calculation. There's no variables, just the one I already know over there that I've already rearranged for on this side to get the displacement. I'm going to take 24.5 times 1.5 and then add that to the result of 1/2 times negative 9.8 times 1.5 squared. So 24.5 times 1.5 is 36.75 meters. And Here I've got 1/2 times negative 9.8, that's negative 4.9. And 1.5 squared is 2.25. And then I'm going to use the calculator now. And I've got 36, I've got negative 4.9. So negative 4.9 times 2.25 is negative 11.025 plus the 36.75, and I get a displacement of 25.7 meters. 25.7 meters. So that is the height of the tower. 25.7 meters. And that answers the question I was looking for. So the important things in this question are recognizing that we can't go directly to the height of the tower because we don't know. What is it we didn't know in this set of equations? What we didn't know was the initial velocity, the 24.5 meters per second. So the way that we got the initial velocity was by recognizing that at the high point of the trip, the final velocity is 0. The initial velocity we don't know. It took 2.5 seconds to do it, and the acceleration is negative 9.8. So we plugged that into the equation describing the changes in velocity, and we figured out that the initial velocity must have been 24.5 meters per second. Once we get that, we can use that with the displacement equation to figure out how far the object, the baseball must have flown until it reached the high point of the tower at time 1.5 seconds.